Hello, in this video we will finally give the proof of the subgroup criterion. Alright, now we are going to prove the subgroup criterion. Remember, the subgroup criterion theorem is an if and only if, which means there are two directions to show. The first direction, you assume that H is a subgroup, and then you show that H satisfies properties 1 and 2, that's closed under multiplication and closed under inversion. That's the first direction we're going to show. And then you show the reverse direction, which is that any set that's closed under multiplication and inversion is in fact a subgroup. So let's begin the proof. First, suppose H is a subgroup of G. We need to show that it's closed under multiplication and inversion. So as a reminder, closed under multiplication means for any x and y in H, x times y is in H. Oh, but that's part of the definition of a subgroup. Remember, a subgroup is any subset that's closed under multiplication with the additional property that it also happens to form a group. So we show that H is closed under multiplication. However, that's part of the definition of subgroup. So you're taking one of the properties in the definition, and, well, it's true. I mean, if you want to claim that a duck is a bird and you let something be a duck, well, since part of the definition of a duck is being a bird that swims in the water, then you have a duck. You have something that's a bird. Since part of the definition of being a subgroup is being closed under multiplication, starting with the subgroup means that property 1's already satisfied. As I alluded to previously, it turns out to get closure under inversion, we actually first need to prove that the identity element of the larger group G is also an element of H. This is more along the lines of the textbook that uses a different version of the subgroup criterion. And so the way we do this is we let E prime be the identity of our subgroup, which we know has an identity element, and we let E be the identity of G. And I'm going to color code them for the sake of being able to follow the proof. Well, inside the larger group G, if we multiply these two elements together, because blue E is the identity of G, when we multiply them together, we get red E prime. This proof is the same idea we use to prove uniqueness of identities. We want to calculate this product in two ways and try to get E prime one way and E the other way, and therefore conclude that E prime and E are actually the same element. If you can do that, well, since E prime was an element of H, and E prime and E are equal, we discover that E is actually an element of H. Well, the trick we have to take advantage of is that since E prime times E is equal to E prime, and E prime is an element of H, we have that this product is an element of H. And so now working in the subgroup H, we see multiplying on the left by E prime is multiplying by an identity, so we must get something that's equal to blue E. And so we see multiplying this, computing this product two different ways, we get two different answers. Those answers must be the same. So it must be the case that E prime and E are the same element, and since E prime was the identity of H, it must be the case that E is an element of H. This proof is a little subtle, and you have to go through it a few times and think about it carefully to completely grasp it. It's often common for the textbooks to actually get it slightly wrong because they skip through these details a little quickly and they just do this calculation, but you have to do it in the right order in order to be able to verify that you're dealing with an element of H. And it's only once you know you're dealing with an element of H that this part of the calculation is even valid. So this intermediate step being finished, we now actually do the part we want to do, which is show that H is closed under inversion, where here the inverse comes from the larger group G. Well, what do? We take an element of H, and we consider its inverse in the larger group G and its inverse in the smaller group H. And what we want to show is that these two inverses are actually the same. If you can conclude that, then, well, if H is equal to G inverse and little h is in H, it follows that G inverse is in H. So it's similar to the uniqueness of inverses proof. And in fact, that's what we do. If you multiply H times G by definition of inverse in the subgroup H, you get the identity of H. But as we just showed, the identity of H is also the identity of G. And if you multiply G by its inverse in the larger group, you also get the identity. So we get H times G is equal to G inverse times G. And so then right cancellation tells you that H is equal to G inverse. So we get H is equal to G inverse like we wanted. And so we see that we've got the two conditions from the subgroup criterion. In other words, every subgroup satisfies the subgroup criterion, which seems kind of nonsensical, but it's worth pointing out that's the reason why we call it the subgroup criterion. So, it would be an unfortunate tragedy if the subgroup criterion didn't actually apply to subgroups. So congratulations, we are not morons and we didn't pick terrible names. Of course, if you recall, the subgroup criterion theorem is an if and only if. So now we need to prove the other direction. Any subset H that satisfies the two conditions of the subgroup criterion gives rise to a subgroup. So now we're going to suppose H, a subset of G, satisfies those two conditions, closure under multiplication and closure under inversion. And now we need to show that H is a group. So we need to show associativity, and we need to show that it has an identity, and we need to show that it has inverses. Well, if you take three elements and you multiply them, one thing worth noting is by closure of multiplication, x times y is an element of H, and y times z is an element of H. And so multiplying these two elements of H gives you an element of H, and multiplying these two elements of H gives you an element of H. So we do get that these two triple products are both elements of H, which is important to note. But since H is a subset of G, it also follows that both x times y times z is an element of G, as is this other product. Oh, but G is a group. So in the larger group, it follows that we have associativity. So it's kind of cheating, because it turns out the reason why associativity holds is because if you actually view these elements as living in this larger set, you already know multiplication was associative in the larger set. In other words, explanation by practical example, if G were the integers and H were the even integers and we were talking about addition, well, how do you know addition is associative for even integers? Well, because if you add any three even integers, well, even integers are integers, and addition of integers is associative. That's essentially what this argument is saying. Of course, now we state this more formally. Since G is a group, and these two products are both elements of G, we have x times y times z equals x times y times z in the larger group. So multiplication is associative. Note that this holds for any monoid G and any subset that's closed under multiplication. H is automatically a monoid. It automatically satisfies associativity. The next step is to show that H has a multiplicative identity. And the most logical choice is to take the identity element from G, the larger group, and show that it's also the identity element from H. but that requires showing that E is in H. And there's a way to do that by using condition 2. Take any element in H. Because you're closed under inversion, G inverse is also in H. Because you're closed under multiplication, G times G inverse must also be in H. So here we're using condition 2, and then we're using condition 1. But the identity is equal to G times G inverse. So we see that you actually get the identity as an element of H. This fact, by the way, is why my version of the subgroup criterion never requires you to show that the identity is an element of H. Because as soon as you're closed under multiplication and inversion, you get it for free. So this comment completed. We see that the identity element of G is also an element of H. And so naturally, by the same argument as up here, if you multiply any element in H by E, you get H. Why? Because you just do the calculation by reminding yourselves that these are also elements in G, and as elements of G, E times any element of G is that other element. So congratulations, H is a multiplicative identity. The final part we need to show is that elements of H have multiplicative inverses, but by condition 2, we have inverses. We're closed under inversion, so the obvious inverse is going to be the inverse from the larger group. So take an element of H. As an element of G, it has an inverse. And based on property 2 of the subgroup criterion, that inverse is an element of H. The obvious calculation still holds, and so the subset H has inverses. And so H is a subgroup because it inherits its multiplicative identity from the group G, and it inherits its multiplicative inverses from the larger group G. And thus we have the 3 properties to declare that H is a group, and since it was a subset of G that's closed under multiplication, that forms a group in its own right, it is a subgroup. So, in conclusion, if H is a subgroup, then it satisfies the subgroup criterion, and if you have a subset H that satisfies the subgroup criterion, then it is a subgroup. This last bit is a bonus, so you can skip this unless you really, really like this material. I learned this as a graduate student, but it's kind of interesting. There's another version of the subgroup criterion where you get to skip inverses entirely. So suppose you have group G and H is closed under multiplication. If H is a finite set, then it's automatically a subgroup. So this criterion does not apply to any of the examples we've studied so far, but it certainly would apply to a lot of the examples we'd be studying in the future. So it's a handy criterion, and you are allowed to use it. But the proof is slightly more complicated, so that's why I'm leaving it as a bit of a bonus. And so what do you need to do to prove this result? Well, you need to show that you're closed under inverses. And that's the part that takes a little bit of thought. So you need to show for any element in H that you have an inverse. The inverse is also in H. And the way we do this is to consider the infinite sequence H, the square of H, the cube of H, and so on. Because H is closed under multiplication, each of these powers of H, little h, is in this subset. And so this entire collection is a subset of H. So if this collection is infinite, then H is infinite. But we're assuming this set is finite. So it follows that this set of powers of little h has to be finite too, which means this sequence can't contain distinct entries forever. Now, this is a version of what they call the infinite pigeonhole principle. Then we apply what's called the infinite pigeonhole principle. We have an infinitely long sequence of envelopes, but we only have finitely many boxes to put them in. You're going to have a repeat. In fact, you're going to have infinitely many repeats. But for this proof, it's enough to only have at least 2. So the point is, this set's actually finite. So there must be a point where the entries repeat. There must exist positive integers I and j, where h to the I equals h to the j, which I can conveniently write as h to the I times h to the j minus I. Well then, by cancellation in the larger group, G, I have E is equal to h to the j minus I. So this is a proof by cases, if for the moment I assume j minus I is greater than 1, then I can factor out this product as h to the j minus I minus 1 times h. Oh look, this element here is the inverse of h, and in G, and inverses are unique. So h to the j minus I minus 1 is h inverse. But it's also a power of h, which means it's in the subset h. So congratulations, your inverse is in your subset. On the other hand, if j minus I is equal to 1, then h to the j minus I is equal to h, which is equal to e. Which means you took the identity element to begin with, which is a silly choice to pick because the identity element is its own inverse. So if you took something that's not the identity, you found an inverse. And if you took the identity element, it's its own inverse. Either way, h has an inverse, and the inverse is in the subset h. The reason why I point this out is for historical reasons as well. The original definition of a group did not include the concept of inverses because it turned out that they were working with subsets closed under multiplication, and they were always finite subsets. And the subsets, or I should just say, from the modern perspective, what they were actually working with were subgroups of a very specific group called a permutation group that we will cover in a few weeks, the symmetric group specifically. And so they got the inverses for free, but it turned out later that it's more important to require inverses as one of the axioms defining a group, because if you want to study infinite groups, you have to require inverses.